In 2017, Earth came across a very unusual object. At the time, we didn't realize it, but our planet had been visited by something that traveled from deep outer space, originating from another star. It was unlike anything we had ever observed before, and it took years for scientists to understand what it truly was. Now, in 2025, a similar situation is unfolding again. Another mysterious object is moving toward our sun. This time, however, we are able to detect it earlier, and the situation may become even more unusual. Let's go back to the beginning. This object is known as Oumuamua. It is the first interstellar object ever detected, meaning it came from outside our solar system. It spent millions of years traveling through space before eventually reaching our system. Despite that long journey, it still caught us off guard. By the time we identified it, the object had already passed its closest point to the sun and was heading back out of the solar system into deep space. Oumuamua was named after the Hawaiian observatory that first discovered it. Initially, scientists believed it was just another comet. However, closer examination showed it lacked the typical tail seen in comets passing through the solar system. That suggested it might be an asteroid. But even then, the object behaved too strangely to be classified as a normal space rock. It was moving at an unusually high speed. This was the first clue that it might be an interstellar object. Everything within our solar system is held by the sun's gravity. Planets, comets, and asteroids all orbit due to this force. To escape the solar system, an object must reach what is called escape velocity, which depends on its distance from the sun. From Earth's position, that speed is about 42 kilometers per second. When Oumuamua was first observed beyond Earth's orbit as it exited the solar system, it was traveling at 87 kilometers per second, far too fast to remain bound by the sun's gravity. This type of path is known as a hyperbolic trajectory. What makes it even more interesting is that before passing Earth, Oumuamua traveled extremely close to the sun, even moving within Mercury's orbit. Normally, such a close encounter with the sun's strong gravity would slow an object down. However, observations show the opposite. Oumuamua actually accelerated as it moved away from the sun. The name Oumuamua comes from the Hawaiian language and means the first to reach out, or the first distant messenger. It is often simplified to mean scout. This adds another layer of curiosity to an already unusual object. If it were simply an interstellar asteroid, its motion should follow known physical laws. According to physics, passing near the sun should have reduced its speed. Since that did not happen, it suggests that another force, possibly originating from the object itself, affected its motion. This makes it unlikely that the object is just a simple rock. Adding to the mystery is its appearance. When observing objects in space, we rely on the sunlight they reflect. Large planets like Saturn and Jupiter reflect significant amounts of light, making them visible even at great distances. Smaller objects like asteroids usually reflect very little light and appear as faint, steady points. Most asteroids are rocky and roughly spherical, so their brightness remains fairly constant. Oumuamua behaved differently. First, it appeared much brighter than expected, suggesting it may not be made of typical rock. Second, its brightness was not steady. It varied from bright to dim and back again in a cycle of about 7 hours. This indicates the object was not round. Instead, it likely had an elongated shape, showing both a long side and a short side as it rotated. Astronomers concluded that it might be long and narrow, similar to a cigar, slowly tumbling as it traveled through space. Another possibility is that the object could be flat and wide, like a disk, also rotating as it moved. Describing it this way might sound unusual, especially when considering it came from another star system. Some might even speculate about more extraordinary explanations. However, rather than making assumptions, it is better to focus on the evidence and allow for logical conclusions. While its shape is unusual, the most significant mystery is its unexpected acceleration. This behavior is what gives some support to more speculative ideas. However, there's also a known explanation for similar behavior in comets. When comets pass near the sun, they often accelerate due to sublimation. Comets are made largely of ice from distant regions of the solar system, such as the Oort cloud. As they approach the sun, the ice turns directly into gas, a process called sublimation, where a solid changes into gas without becoming liquid. This creates the glowing cloud, or coma, around the comet, along with its characteristic tail. There is also a significant amount of dust released as the ice undergoes sublimation. The key point is that all of this outgassing acts like a natural propulsion system, similar to a spacecraft thruster. If the sun heats one side of a comet, more gas is expelled in that direction, creating a force that pushes the object and alters its path and speed. However, Oumuamua showed none of these typical comet features: no coma, no tail, and no visible signs of outgassing. Despite this, it behaved in a way that closely resembled a comet, which led some to speculate that it might even be an artificial object using propulsion. Now, let's consider where Oumuamua came from. Its trajectory points toward the star Vega, the brightest star in the constellation Lyra, visible in the northern sky. Vega is not just any star. It has been studied extensively and is often considered one of the most important stars after the Sun. Interestingly, around 14,000 years ago, Vega served as Earth's North Star, a fixed point in the sky used for navigation since ancient times. Due to the gradual wobble of Earth's axis, the North Star changes over time. Currently, it is Polaris, but it will shift back to Vega around the year 14,000. There is no direct evidence that Oumuamua originated from a Vega system. It simply arrived from that direction, which also happens to align with the direction our solar system is moving through the galaxy. In a sense, the encounter was mutual. We approached it as much as it approached us. As Oumuamua passed around the sun, it briefly traveled toward Earth, adding to the sense of coincidence. Although close in space is relative, its nearest distance was about 24 million kilometers. For comparison, the Moon is roughly 400,000 kilometers away, making this about 50 times farther. It's possible that even at such distances, advanced observational technology, if it existed, could detect us. Our telescopes first observed Oumuamua a few days after its closest approach, by which time it was already leaving the solar system. As a result, we had very limited opportunity to study it in detail or determine its exact nature. There have been proposals to send a spacecraft to intercept Oumuamua, but this would be extremely difficult. The object is moving very fast and already has a significant lead. No conventional chemical rocket could catch up. A mission would require complex orbital maneuvers, such as traveling to Jupiter, using its gravity to redirect toward the sun, and then accelerating near the sun to gain enough speed to follow Oumuamua's path. At present, such a mission is not practical. If Oumuamua had been the only interstellar object ever detected, such an effort might have been justified. However, soon after its discovery, something unexpected happened. We detected another visitor. In 2019, a second interstellar object was identified, named Borisov after the amateur astronomer who discovered it. Like Oumuamua, Borisov followed a hyperbolic trajectory, moving too fast to be captured by the sun's gravity. It also came from a similar general direction in the northern sky, this time from the constellation Cassiopeia. Unlike Oumuamua, Borisov clearly behaved like a typical comet. It had a visible coma, a tail, and appeared to be made of materials similar to comets found in our own solar system. While still fascinating, it did not present the same level of mystery. What is particularly interesting is how suddenly these discoveries occurred. For a long time, we observed no interstellar objects at all, and then within just 2 years, we identified two, and soon after, a third. This newest object is called 3I/Atlas, meaning the third interstellar object detected. It was discovered by the Asteroid Terrestrial Impact Last Alert System Atlas, an automated survey designed to detect near-Earth objects. It was first observed on July 1st at a distance of 4.5 astronomical units from the Sun. An astronomical unit, or AU, is the average distance between Earth and the Sun, used as a standard measurement within the solar system. This means 3I/Atlas is about 4.5 times farther from the Sun than Earth, placing it beyond Jupiter but still far from Mars. What makes 3I/Atlas especially interesting is that we detected it while it was entering the solar system. We are now able to observe its approach in real time. Early observations showed that it is both large and extremely fast, faster than Oumuamua, and it is coming from a completely different direction. While Oumuamua and Borisov approach more directly, Atlas is entering from the side, suggesting it originated from a very different region of the galaxy. To understand this better, consider the structure of the Milky Way. It is often shown from a top-down view, with our solar system located roughly halfway between the center and the outer edge. However, from our actual perspective, the galaxy appears more like a side view. It has a dense central region, called the bulge, surrounded by a flat, rotating disk of stars, gas, and dust arranged in a spiral pattern. Most stars are concentrated in the thin disk, which is where our sun is located. Above and below this is the thick disk, a less dense region containing older stars. Because there is less active star formation in this area, objects found there are often remnants from the early stages of the galaxy. Beyond that are globular clusters, dense groups of stars that exist outside the main disk. This is important because 3I/Atlas appears to have originated from the thick disk. If that is correct, it could be an extremely ancient object, possibly over 7 billion years old, older than our solar system itself. This alone makes it highly significant. There are two additional factors that increase interest in this object. The first is its size. Initial estimates suggest it may be up to 20 kilometers in diameter. Continued observation has also revealed that it has a coma, a surrounding cloud of gas and dust, indicating that it is not a solid object like Oumuamua, but rather an interstellar comet, similar to Borisov. So, the coma is about 20 kilometers wide, while the nucleus, the solid core of frozen material at the center, could still be as large as 11 kilometers across. That would make it roughly 10 times bigger than Oumuamua and about 5 times larger than Borisov. In other words, these objects appear to be increasing in size. The second point, and perhaps the most unusual aspect of Atlas, is its trajectory. Since this object is approaching from the side, it will pass near several planets during its journey through the solar system. Its closest encounter will be with Mars, at a distance of around 28 million kilometers. After that, it will pass relatively near Venus at about 97 million kilometers. On its way out, 3I/Atlas will also pass by Jupiter at a distance of approximately 53 million kilometers. This gives a unique path through the solar system, almost like a broad survey of multiple planets. However, despite these close passes, Atlas will completely miss Earth. At the time it moves through the inner solar system, Earth will be on the opposite side of the Sun. As a result, our telescopes will lose sight of the object in October this year, and it will not become visible again until December. By that time, it will have already made its closest approach to the Sun and will be heading back out of the solar system. Similar to the unusual behavior of Oumuamua, some have suggested that Atlas following this multi-planet path is not random, but rather intentional, possibly the action of an advanced probe gathering data while avoiding direct observation from Earth by staying hidden behind the Sun. Even when considered openly, that explanation seems unlikely. If an advanced civilization had sent a probe across interstellar space over billions of years and had the chance to closely observe a life-bearing planet with an advanced civilization, it would be unusual for it to avoid direct study at the final stage. What makes 3I/Atlas particularly valuable is that we still have time to observe it as it moves closer to the inner solar system. Over the coming months, much of the current uncertainty may turn into clearer understanding. Unlike Oumuamua, there's also a small possibility of intercepting Atlas. While launching a new spacecraft in time is unlikely, there are already missions orbiting Mars and Jupiter. In theory, one of the Mars orbiters could adjust its path to approach Atlas. There's even a scenario where the Juno spacecraft could leave Jupiter's orbit and attempt to meet Atlas in deep space next spring. While this is not very likely, it will provide direct data about the object. If a similar mission had been possible for Oumuamua, we might have far more answers today. Even without direct contact, scientists have developed reasonable explanations. Assuming Oumuamua was not an artificial object, it could still have been a type of comet. Comets are essentially made of frozen materials, but those materials are not limited to water ice. In our solar system, most comets contain frozen water, which sublimates into gas and creates a visible tail because water vapor is easy to detect. However, not all gases are visible. Nitrogen, for example, makes up nearly 80% of Earth's atmosphere. It is colorless, odorless, and difficult to detect directly. One well-known object composed largely of nitrogen ice is Pluto. Much of Pluto's surface is covered in frozen nitrogen, which is highly reflective. This reflectivity is one reason Pluto appears relatively bright when observed through telescopes, even though it is less than 2,500 kilometers in diameter, smaller than Earth's moon. Now consider a possible scenario. Pluto, or a similar object, is struck by a large asteroid or a rogue planet and breaks into many fragments. One of those fragments is ejected at high speed toward the inner solar system. This fragment would essentially behave like a comet, but instead of water ice, it would consist mostly of nitrogen ice. As it approaches the sun, the nitrogen would sublimate into gas. However, since nitrogen is invisible and does not produce a visible tail, we would not detect the usual comet features. Despite this, the outgassing would still occur and act as a propulsion force. As the object moves closer to the sun, more gas will be released, increasing this effect. Combined with the sun's gravity, this could accelerate the fragment and eventually eject it out of the solar system into interstellar space. This type of object would match many of the observed properties of Oumuamua. If a similar event occurred in another star system, possibly in the direction of Vega, it could have produced a fragment of frozen nitrogen that eventually traveled into our solar system. Such an object would likely behave and appear similar to Oumuamua. The alternative idea is that it was an artificial structure, but that explanation requires far more assumptions. This is why studying 3I/Atlas is so important. With more observation time, we can reduce uncertainty and better understand these interstellar visitors. These objects offer insight into processes that occur on a much larger scale than our own solar system. They provide an opportunity to learn how matter moves and evolves across the galaxy. The most valuable discoveries are likely still ahead, so continued observation will be key.